Okay, so here it is. So we wish to understand the origin of life. I told you probably uh, it's a possibility that this is not exactly science, because maybe the life arose with just by chance. So we are the least possible probability, lowest probability, only one planet in the whole universe. So it's not science if it's only once. But in any case, there is some clues that make us to think or to hope that this could be a science. And so if it is science, so we should know. So that means that if we mix the correct compound, we treat with the correct, I don't know, um, we cook in the some way, we can we can create life. Also, we can start something that is important, that is beyond all this life, that is some selection. So some nowadays we call the natural selection. So the improvement of this material. Then, okay, I don't want to stress too much now on this topic, but also thermodynamics is involved, of course. And so, but nowadays I will try to find some relationship that we can, so some the basic sciences that can help us to move toward the direction of discover on how the life arose. And so we should go to the maybe hard sciences like physics, chemistry, or biology. So maybe I'm missing some other sciences that could be useful to for this goal. But in any case, we started from this. And as you know, on the basic chemistry, basic physics, basic biology, so the biology is from the other side. Physics, chemistry, maybe they are far from a living organism. They can have some clues of the working or something else. But in any case, it's difficult to find a match. So it's really, so that the origin of life science is really an open world, it's an open field. Nobody knows exactly which mixture of science we have to use. For sure, we have to think out of the box. For sure, we have to make all of this knowledge to cooperate, because nowadays we call physics, biology, chemistry, but okay, science is only one, but who is able to think in the different way? So it's only with the cooperation of people coming from different basic knowledge that we can find and so go toward the final goal, that is to understand how the life, which are the origins of the life. And so starting from the basic science that I told you, we can have some parts of these sciences, some interaction between them that goes toward the direction of this. For example, as you know, the biology, you can have the synthetic biology. Also, one PhD student from here was working with these circuits, genetic circuits or metabolic circuits. And so you can modify the organism. Now our knowledge of the biology is very deep with respect to only a few years ago. And so we understand the path, the reactions, so the metabolism. So we are close to the chemistry. We know the metabolism. We are able to alterate the metabolism. We are able to change the genes. So we can modify the biology. And maybe if we think we can go toward the origin of life, maybe. So this is a possibility that is possible. We can try to decrease the complexity of the actually living organism. Maybe we are moving in that direction. And so for related to physics, we have a connection with the biology. Physics and mathematics also, because the metabolomics and also the genes, they are regulated. So we have some networks of interaction. And physics can help to solve these networks. So here between physics and biology. Also, we have many overlaps in between physics and chemistry. I never mentioned here the thermodynamics, but okay, we'll see. But in any case, so why I wrote here photochemistry, radiation chemistry? Because here, on the planet Earth, we have life because we have the sun, and the sun is able to give us some useful light that is harvested by plants, and so the plants will reduce the entropy. So it means increase the complexity of this. And thanks to plants, we are here. So the animals survive because plants are able to convert the energy from the sun to something more useful. So at some stage, the photochemistry is important because it nowadays it's the reason because we are speaking now. So because we are alive, so the light is converted in some very ordered molecules and reaction mechanism. And so maybe this is the key for solving this. So for the photochemistry, we need also the physics and the chemistry. And also I mentioned here radiation chemistry. It's more general than photochemistry, but usually radiation chemistry involves some photons having higher energy, starting, for example, from X-rays or gamma rays or cosmic rays. So it means that now you are understanding that I'm moving from planets in which you have photochemistry to maybe some part of these outside planets, maybe in the interstellar medium, I will see. And also, as far as we know today, so the life so it's present on a planet. So we need maybe we are not sure, but possible a planet is a useful maybe pot in which we can have some interesting chemical reaction. And so the planetary chemistry is important. The planetary chemistry derives from the physics. So the mass of the planet, the composition of the planet, the distance of the planet from the star, the type of the star, all these variables can make us understand which chemistry we can have in the planetary chemistry in this planet. So maybe we can find, for example, liquid water. And because as far as we know, the liquid water is so important for the life. And maybe this is not only the possibility that we have, but in any case, scientists, physicists, they are astronomers, they are looking at the stars, finding new planets close to the stars with the different techniques. They are improving year by year. They are because up to that's maybe 10 years ago, we are able only to understand very big planets that are close to stars that maybe are more than 100 light years from here. Uh, because how they understand that you have a planet on the star. So you just measure the light coming from the star. And if a planet passes over the star, you have a decrease of the light. So making a possible calculation, seeing if periodically this happens, you can understand the mass of the planet. And so you can understand, for example, if you have a planet that could be useful for the life, because even in our in our solar system, so the planets we know more because many probes we sent to measure this planet. We know many of the planets on Earth, sorry, the solar system, like Jupiter, or Saturn, or Neptune. They are made by gas. So gas maybe is not so useful for keeping the life. Also, they are far, they are very cold. And if we wish to have chemistry, we need to have some source of energy. Maybe photochemistry can help, who knows? But in any case, planetary chemistry is very important to make us to understand how we can have the prebiotic, the life origin. Also, I mentioned here the system chemistry. What is the system chemistry? So maybe someone knows the systems biology. System chemistry is quite new because chemistry, so usually chemistry in the lab, chemists in the lab wish to take reaction A, so compound A, making the reaction with B, obtaining only C. So imagine you wish to prepare a drug for some treatment, you need pure C, you need no more. So you don't want to have C, D, E, etc. You need only one compound. So usually chemistry is interested in finding the way to synthesize, to prepare the compound that you want. But now for the origin of life, it is not like this. We wish to move towards some metabolism. So metabolism is a complex network and of chemicals, of reactions. And so maybe this approach is not so useful. So you need a different approach, an approach that is able to work on arrays of reaction, many reaction interacting together. So you need the system chemistry. This is quite new. Not it's a growing field, but it's difficult because as Merli, for example, spoke the last time, since he's an analytical chemist, he knows better. So if you have, for example, one extract of a plant extract or a coffee, so now you're drinking a coffee, if you make separation, maybe with the chromatography, that is okay, means to separate molecules. In the coefficient, maybe you have some thousand compounds, more or less. And so it's only a part of a plant. So if you want to make some chemistry with many compounds, maybe you have to analyze 10,000 compounds. Which are the techniques to do this? Oh, we have not many, so they are expensive. So you need to create the system chemistry. Maybe from the point of view of biology, you have already some possible technologies to do that. But for the chemistry, this is not like this. So we have to prepare to make some experiment to prepare even more new instruments to do like this. But in any case, so we are trying to move toward the origin of life. But in any case, we don't know how far is this. And so we can represent maybe in another diagram like this. So we put a complexity here. So exactly the complexity, what it means. So if you are maybe a physicist or chemist, maybe you prefer entropy. So you are going toward the low entropy. That it means the high order, because a living system is very ordered. Because if you think we have the DNA, so the sequence is perfect. So if we have adenine, thymine, guanine, and so on, the sequence is almost perfect. You repeat the sequence perfectly every time. So the error is very few. So you're missing maybe one molecule over some trillion molecules or more. Even the transcription of the DNA into RNA and then proteins is almost perfect. So it means that we are, so the living system are so big with respect to atoms because they are so complex. So maybe you can't create one living organism with few atoms. You need more. So maybe we are so big because we need a lot of atoms that creates cells, that creates the human being. And so we are complex, starting from molecules up to the scale of meters. It means several trillion or more, 10 to maybe to the 20 or 20 to the 25 atoms, more or less. So it's a huge thing. So everything is ordered from molecules up to the big scale. And the chemistry, so they are poor with the physics. So they start with a few molecules. Okay, chemistry can build, for example, peptides. They can build DNA, RNA, because these techniques are used by a biologist to create this. But there is a big gap between this and the living transition, how we can speak. So we have following two different approaches. The bottom up, so from the simple to the complex, and the top down, that it means from the complex to the simple. So biologists wish to simplify the living organisms, the actual living organisms. The chemists and physicists, they must complexify this. So, but we are looking for this living and non-living transition. We don't know exactly the position of this, because also we have to define what is live, what is not. So I don't want to speak about philosophy today. So in all my presentation, I will try to avoid to speak what for me is living, what is not living, because a virus is living or not. a molecule is living or not. It depends on what you think about this. Then maybe we will see what chemists think that could be living and what biology think. But we don't know to find an answer of this open problem. So we leave this to some philosophers. Okay, but first of all, we are speaking. So always interested how the life arose, how which compounds have to choose, what have to mix. But the correct question, the first question is when the life arose. So when can life arise? So this is another question. So now the current theory is that the universe, the whole universe came from the Big Bang. So this is a theory, you are a scientist. So you know that maybe tomorrow this theory is wrong. But up to now, this is the actual theory that we know. And so all observation make us to think that the Big Bang theory is correct. So the Big Bang means that everything started from something unknown. And after that, you have a big expansion. So the creation of all the things that we are seeing today. So now we are more or less here. So 15 billion years starting from the time zero, that is the Big Bang. Even not known exactly what is the meaning of the Big Bang. So nobody knows. Maybe it's something related to quantum mechanics, but scientists are not all together in the same thinking. So if you see the scale here, so if you want to the life, you need to have the possibility to create complexity. So you need atoms, for example. At the beginning, there wasn't. So the beginning, okay, you have to wait maybe 3 minutes, not too much for us. But you see, to create the atoms, and so the universe become transparent, because before here this time the universe was not transparent, so light cannot pass, cannot exit. But okay, after the atom formation, you have the release of the photon, and you could start to think about some more complex. But here after the Big Bang, you haven't so many atoms. So nowadays we know also we are able to build some atoms. We know maybe 118 different atoms that we call elements. But after the Big Bang, you have mainly hydrogen and helium. So from the chemical point of view, it's so boring. Maybe you have some lithium, but it's so boring. So not much chemistry. Even even if you're not a chemist, you know that this helium is a noble gas, so it does not react with anything. No reaction with this. So only hydrogen. What we can do only with hydrogen. Then what we can do with hydrogen, we can make stars, and this is the beginning. This is an important point. We can make stars, and then we have to wait that the stars create other elements. And so when the life can arise, so it cannot arise before the starting of the complexity. So we need some elements, more than hydrogen and helium. Even it's not visible here, but we need also the correct temperature, correct amount of photons and so on that are present in the universe. Okay, then, okay, now we are speaking about the beginning, so we think about the end. So how long the life can survive? Because we need the complexity. But we know maybe that the universe, so the entropy of the universe is increasing. So it's called the second principle of the thermodynamics. So the entropy is increasing, and that means that while you wait, the universe increases the disorder. It means that after some time, the life cannot be any more possible. But we have not to think about this, because our sun will die maybe after a few billion years, something from now. So nowadays, the Earth is 4.5 billion years old, more or less. But few billion years, maybe after 1 billion years, starting from now, the sun will increase the amount of energy released by 10-20%. And then it will finish the hydrogen. It starts to, so the nuclear fusion created from hydrogen, it creates helium. From helium, you create heavier elements. but our sun is not too big, so it's not able to burn the helium with a in the so good way. So the sun will become a red giant. It means that the volume of the sun will increase a lot. So probably, so the top part of the sun will come close to the Earth. But before this moment, all the Earth, so the elements, the water evaporates for the high heat that you can receive from this. So we know that after few billion years, the Earth will be no more habitable. Maybe the Earth will become like Mercury. It's like a rock at 500 degrees, so cooked with no water, only with so even with the pressure of the sodium and other lighter element. Also now I made some mess here, but okay, I think it's visible. So okay, maybe the life can so the could be in another planet, another star that is not still formed now. Okay, but in any case, we are going. So the universe is become older, so the entropy is increasing, and so after some time, you have no more stars because they are eaten by black holes. So you will have after this a dark era. So no more star, only black holes. They are eating themselves. They are growing, 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 and then after that, you will have the evaporation of these black holes for the Hawking radiation. So there's a theory. So the black hole is not stable. It make release some low energy photons depending on the surface of the event horizon, so the size of the black hole. So bigger is the black hole, more is the evaporating. But what is the speed? It's like zero speed. So because nowadays the universe has 10 to the 10 years, you have to wait 10 to 100 years for the complete thermal death. So this is a thermodynamical death. So it means that more or less all the universe has the same temperature. At this for sure, but before this time, you cannot do anything. You have nothing possible. Even you cannot measure the time because the time is so strange. It's not like the space. For the time, you need to create a clock. So a time is something that is measured by the clock. The clock is a machine. It needs some energy. It needs some complexity. So if you are close to the end of the universe, you have all the atoms or photons at the same energy. You cannot even create a clock. So the asking what time is it is no meaning. So the universe will will end with something that is impossible to know. So, but in any case, we will die even a lot of time before this end. But at the end, even the asking the time is no meaning, like in the beginning of the Big Bang. So the timing before the Big Bang does no meaning asking the time before it, because there is no time before the Big Bang. And at the end of this thermal death, it's no way to speak to define what time is it. Okay, but we come back now to the theories on the origin of life. And okay, you see two hypotheses. In any case, one does not exclude the other. So some scientists like one, the hypothesis A, the other scientists like the hypothesis B. So what it means, the hypothesis A is extraterrestrial origin. So the life originates outside a planet. So it's outside our planet, but in any case, it's also planets. It's coming from the outside. And this is called Panspermia. This was a scientist, was the first one speaking about this, was Svante Arrhenius, a famous physicist chemist that lived many years ago. And so more or less this panspermia, this theory, I don't know why, but physicists likes this theory. So the panspermia. You can have the random panspermia, means somewhere in the universe you have the creation of the life, or directed means that it's coming from somewhere. Or when you have the hypothesis B is it written terrestrial origin? We can write maybe planet's origin. So you need a planet for this. And so this is the option B selected by chemists. chemists like more this hypothesis because chemists work with solutions. So they work with a solvent with some molecules inside. Usually solvent could be water. So they like the liquid water. So in the space, how you can have liquid water. So they like more this hypothesis. And for this, they divided in two. So you can have organic origin. Organic is another name is invented by chemists. So the organic origin means that you need some complexity due to some carbon compounds. And then you have some inorganic origin, means some one origin derived from rocks, for example, or clays, because chemists call inorganic, for example, compounds having silicon, oxygen, aluminium, and other metals. So this is called inorganic. Also, it's noteworthy that the inorganic origin can be divided by clays and pyrites. So different areas they will divide, they will divide again. Okay, so now also this theory belong to at the end some energy source is necessary, and the energy source could be so it means one organism in order to be alive should, so we are alive because we eat and we drink, we so we produce wastes, we breathe. So we are using some energy, we are using some matter from the environment, and we produce a lot of entropy with respect to us. So we produce a lot of disorder in order to maintain our order. So we need a source of matter and we need a source of energy. So this, you see, we are in the middle. So these hypotheses are both from the extraterrestrial and terrestrial origin. So if you need a life, you need the source of matter and you need the source of energy. So the energy could be delivered by extraterrestrial or terrestrial. So this is for the matter. The energy for photosynthesis or chemosynthesis means that you are using some chemicals, you are converting some chemical to produce the energy. So, but the problem is maybe the all this is correct. So we can have a mixture also of all these theories. So it's like now we are speaking about the ingredients, but the recipe is not known. So we know maybe where to start. Okay, you can have an idea where to start, which ingredients you have to take, but you don't know how to mix. Okay, if you maybe you see one recipe, you understand easily because so oil and garlic, onion, so on. You easily maybe can build the recipe. But if you speak about having a lot of elements, a lot of possibilities, okay, maybe you have ingredients, but how the recipe is there a recipe or not? Who knows? And in any case, as I told you, we have to wait some time after the Big Bang because we need the first star having only hydrogen and helium. The star starts burning these elements with the nuclear fusion. They create heavier and heavier elements. But this happens up to the iron. When the star, if you have a big star, not like the sun, but bigger, able to make the nuclear fusion of these elements, when you reach the iron, you have a big problem because if you try to make the nuclear fusion of iron atoms, you haven't the release of energy, you have the absorption of energy. So the core of the star cools down. It means that the external part of the star collapses due to the gravitational force. And so you will have a blast. So all the residual elements will burn in some chaotic and energetic things that is called supernova. And you can have the production of many other elements. This is an example of the element that can be produced, and the amount in the part per millions. You see at the end, if you see, always you have abundance of hydrogen and helium, but some oxygen, carbon also present, and you can goes up to heavier element. Nowadays, theories thinks that the heavy elements like platinum, gold, mercury, they are produced by different not supernovas, but maybe the collision of neutron stars. Okay, in any case, we need to give time to the universe to produce some useful element for us. And because if not, so we have always hydrogen with a little bit of helium that's completely useless. And but okay, let's see here. So now we have some oxygen with carbon. So maybe we can start to play something. Neon useless again because it's a noble gas. Okay, so but with chemistry can we have with these elements? So where we have to look? Maybe you already seen these pictures in your life, isn't it? Have you ever? So is there someone that is able to recognize some of this structure that I'm showing you? What are these? Someone knows this?
Is it the pillars of creation? It doesn't look like it. The Eagle Nebula.
Yeah, so these are nebulas. So this is called the Interstellar Medium. I'm seeing that someone is writing to the chat. Yes, they are nebulas, but it's they are very famous because this is called the crab nebulas. This crab. Look at this. What it looks like. It's like the head of one animal.
Cobra.
Horse. This called the Earth's horse head nebula. This is called the Lyra Nebula. Did not know meaning for this, but this nebula so you have something more. So here you have maybe some particles, some gases for sure, and this is not belonging to the stars. As you see, for some of these nebula, it's clearly visible that they are coming from some huge explosion because you see the external shock wave. So maybe there was a star here that exploded, and this is the external shock wave. Even for this one is like spherical. For this, you need to think something more different, like the smoke. So the smoke, when it reduces the speed, it creates some random field. So they are just big parts of smoke. Smoke is interesting because smoke is it has also solid particles. So let's see. So we are speaking about the interstellar medium. So just not interested, not too much to stars. They are too hot. Even you have a lot of elementary particles, so impossible to think about something useful for the origin of life inside the star. Maybe the star is useful, but inside no. And so we need something that is colder, that it has more element, and this is the interstellar medium. The interstellar medium is just one word telling that. So it's the medium, so what you have in between the stars. So not so interesting maybe, but so if we wish to go, so if we are in the solar system, we are more or less here. If we are in the solar system, we are maybe not so in the interstellar because we are close to our star. So if you want to go into the interstellar medium, you have to exit from the influence of the star. And so what we are speaking about. So now we have the sun here, and the sun from some 5 billion years is burning the hydrogen, so producing a lot of energy, producing solar winds and magnetic fields and particles that they are ejected everywhere. So this particle is like the solar wind, and so they travel at high speed. They're able to overtake all the planets. They go further. But at one time, they reduce the speed for sure, because they are encountering other particles. They are reducing the speed. Here you have at one maybe part, so on the surface, you have more or less the speed of this particle is very reduced. It's so slow. They are slow. They are going to stop. And so here you have a difference. So you imagine because more or less we think that we have vacuum in between the stars and so on. Okay, maybe here we have vacuum, but we have solar wind inside here. So particles coming overhead. Here is different because outside the influence of the sun, you have something different, the interstellar medium. And so the sun is blowing away the other particles. It means here inside you have more vacuum with respect to the other, because here you have the pressure due to the particles emitted by the sun, keeping outside the other particle. So we know from my measurement, but also we send probes. So two of the probes sent 40 years ago, they are exiting the influence of the sun. So they are reaching the interstellar medium. And so what they observe an increase in the number of particles, because here the particles is like they wish to enter, but they are blown apart by the sun. Here they stop, so you're almost zero. Here the influence is very low, and also the particles from the sun try to come back, change the direction. Here you have maybe some situation that is chaotic. They are going to measure with these probes. Then you have the interstellar medium. So we know these probes are going to go outside so they will, for example, travel 1.6 light years. So in the next 40,000 years, but maybe in the next 10 years, 20 years maximum, the energy of the Voyager and 1 and 2 will finish. Energy that is not given by solar panels because they are too far. So the sun here is appearing like a star, like other stars that we are seeing. Not possible to have energy from the sun at this distance. Even nowadays everybody is speaking about the Perseverance rover, the other stuff. Even on Mars, not so far from Earth, even on Mars, the light coming from the sun, the energy is like 1/3 with respect to the Earth. So the solar panel will give you less energy. So you use some nuclear powered energy. So these probes use the same. So in the some years they will finish the radioactive isotopes that they have inside. So they will finish the energy. So they will stop leaving, they stop transmitting data, but they will continue their travel. For sure, they will decrease the speed because here they are meeting more particles. So what we know from these probes, so we measure this. As you can see, there is a neat difference. So this is okay, yes, it's written in German, but here you see the two probes exiting, and this is the number of particles. You have a steep increase in number of particles here, maybe less. But in any case, you see a change. Here we are inside the influence of the sun. Here we are exiting. So here outside, you see it's different. Also, we have many change. And so the measurement, also they are measuring also the magnetic field. So it's a complex part. So what we are speaking about, so we are speaking, so the probes are more or less like here in this part. So the Pluto is here. We are here. Okay, as you can see, to reach the star, closest star that's just few light years from us, you need to reach 10 to the 5 times so 10 to the 3 with respect to the far, so the distance that is covered by these probes. But here you have the interstellar medium. Here not, because we are inside our star. So how we know what is present in the interstellar medium? For sure, we cannot go back, take a sample. Not possible. Unfortunately, it's too far. And so we can use some radio telescopes. Why radio telescope? Not microwave, not visible, not even because we have an atmosphere. And also, as you know, if you maybe have the visible light, you have the radio wave. So the frequency of the radio is lower. So it means that it's stopped less. So if you have one object of the size of the wavelength, it will reflect the light, more or less. And so if you wish to see inside the nebula like this, so you have dust, you have particles for sure, and then this size is so big. So the light, so the visible light maybe is not so useful to understand what you have inside. So you have to use the radio waves. And so you are making some spectrum that are not only vibrational, but roto vibrational spectrum. So you should usually in our laboratory, it's not you haven't this, if you are not working exactly in this field, you haven't this kind of apparatus to measure this roto-vibrational spectrum. So you need some radio telescope. This is the Arecibo telescope. So now it's that, because this just last year, this part fell apart and so broke everything. But this was the biggest radio telescope, more or less. You have the diameter of this, so 300 meters, because bigger is the dish, higher is the amount of radiation that you concentrate inside your measuring point, this one. But nowadays, okay, we haven't lost too much. So maybe a piece of history, because this was used, this was created actually to search the life in the universe. So this telescope was built by NASA and other people because they wish to check if we can get some radio transmission from the universe. Maybe someone is transmitting some audio, video. And so I see one question. NASA SETI, yes, you're right. SETI is search for extraterrestrial intelligence. So it is a program. Okay, but nowadays, so we don't want to build a bigger. Even for this, it's so difficult to maintain also, because now they break. And even you cannot move this. So this is places somewhere on the Earth. If you want to point to some other star, you have to wait the rotation of the Earth. So you cannot move this, too big. But nowadays, we have a different technology that is called interferometry. Interferometry. So they are radio telescope, but you have array of radio telescope. You have many. And so they are spread over a field. And this radio telescope act like a bigger radio telescope that is more or less like the surface covered by the radius of this. How it works. So the problem with all the measurement, if you are a physicist or a chemist, when you have a low signal, it's covered by noise. And so if you have this signal, transform, so remove the noise, is a difficult task. But okay, now how it works. So the signal is coming and it's covered by noise. But so the signal is coming in all the same antennas, maybe with some time. After some time, because they are far, they are close. So you can calculate exactly when the pulse will come. And what you know that the noise from this one is different from the noise of this one. So the signal is the same, the noise is different. So if you treat the signal, you are able to mix many and to recover the starting signal. So it's easy to speak like this. It's so complex if you build like instrumentation like that. So if you want something bigger, okay, you need to put some radio telescope all over the Earth. So now let me delete some of my, okay. So if you need something bigger, just spread the telescope all over the Earth. So if you do like this, you see even in the remote zone of the Earth, you can make this radio. It's like having a big radio telescope like this, more or less the size of the Earth. So what you can expect more? So what you can do with this radio telescope? So why you need a bigger? So if you have a bigger radio telescope, you can see far, so small objects that are far. And so with this, you can see very far objects. So what we can see with this radio telescope, what we need. This is maybe one of the most known picture of the last year. This is the picture of this year because they make some other elaboration. Have you ever seen this picture? I hope yes. They created also a meme. Have you seen already?
Yes, Prof. This is the black hole image
Yes.
for the by the theoretical calculation.
Yes, so they measured this with this radio telescope. They make several calculations across years, not only for minutes. Also, what it means that you have the sun here. Someone is writing. Okay. If you want, you can switch on the microphone. It's not a problem for me if you stop me, so don't worry. Because for the chat, sometimes I'm not able to see. If not, open the microphone, speak. Okay, so we have the sun here, we have the Earth here. Now the radio telescope is big as the Earth, but the Earth, after 1 year, makes a revolution. So it means that if we measure across over the year, we can, in line of principle, have like a radio telescope, not only bigger than the Earth, because if you are able to treat this data, to put together in the correct way, treating the mathematical way, so we could make signals coming like having a bigger radio telescope. And this is how they produce this image, because this image is the center of a galaxy. So the center of the galaxy is crowded by everything, a lot of stars, a lot of objects, a lot of nebulas. So the only radiation passing through is the radio waves. So that's why you are using this. So, but like to make you to understand how they obtain this image. So they collect data for 5 years, I don't remember. They make like 1 petabyte of data more or less, or some petabyte of data. They make the calculation with all this data, they create this image. And so to letting you know how is the resolution of this telescope. Okay, imagine the Earth and the Moon. So you put the orange on the Moon, and so you're able to see the peel of the orange from the Earth. So this is the resolution. It means that the Moon is here, the Earth is here, the orange is like this. It means that you are going to see one angle that is so short. So it's impressive so the resolution of this. This also black hole is so impressive. So it's very far. So 53 mega light years. So billion of light years. But it's so huge. 6 or 7 by 10 to the 9 times the mass of the sun. So it's a huge object. And so you can understand a lot of physics inside here. These lines are related to the magnetic field. And also this, for example, this is the galaxy, the M87 galaxy seen by the radio waves. The black hole is there in the center of this square. And if you enlarge image, you see this part. This is a jet emitted by the black hole. And the jet is changing because you see from 2012 to 2017, this part is changing. So it means the black hole is ejecting particle at the speed, it's 99% of the speed of the light. So huge energy here. So you will destroy everything. The jet is coming toward us. If this could be closer, they will make evaporate the entire solar system in just like a blowing on the candle. So these are the energy that are present on the universe. So the volume is so huge, so impressive. And so, but let's go back. So because we need lower energy to have something useful. So we can make some to put something, also to make some classification of the interstellar medium. And so yeah, the classification is like molecular clouds. You see here the name. But here we have interested maybe in this part, in the temperature and the density. These are important parameters for us now. And you see the state of hydrogen. So hydrogen here in this cloud is molecular, it means like this. In this, the second, they are natural atomic, it means they are hydrogen radicals. Here you have ions. Yeah, still hydrogen present under ions, but also metals are ionized. So you have the iron that's ionized, also other metals. So the energy is increasing. You see, well, the parameter giving you the idea is this one. The temperature is in Kelvin. So molecular clouds, where you have the hydrogen, it's a molecule. The other are just atoms or ions. The temperature is quite low. So 20 Kelvin is a little bit cold. It's only 20 degrees of difference between the zero. Here you have the cold, medium, neutral But you see the hydrogen no more stable in these conditions. The warm, see this, from 6,000 to 10,000 degrees, and okay, this is Kelvin, more or less the same. And it means that here in the solar system, this temperature is at the top part of the sun. That is the hottest part of the, not hottest, but the part, the external part of the sun, it has this temperature. So you can understand that you cannot have anything complex at these temperatures. Even see a temperature, even this more million or 10 billion of degrees. So it's like temperature we have almost in the center of the star. And also the density of particles is interesting. So see the number of particles over square centimeters. Usually here we have a lot of particles on square centimeter, maybe 10 to the 20, something like that, for a normal solid material. You see this so-and-so is quite good. This one, 10 to the 2 is like gas, diluted gas, low pressure gas, but still you have some molecules. Here you're decreasing a lot, the number of molecules. Even here you're almost the vacuum. Also, you can have the techniques that you use to measure something here. You see radio and infrared are the techniques that are used more or less. Just to show you what we are speaking about. So where is this interstellar medium? So first of all, imagine one star that is bigger and hotter than the sun. And so in the first part, you have a region. It's called H2, H second. They are meaning this is like a Roman 2. It's it calls H2 region, but it's not related to H2 like chemist says, but related to H plus. So here, no chemist here. Starting from this, you have neutral hydrogen again, you have less chemistry, only hydrogen atoms. Okay, just to show you the density. So if you take the Earth's atmosphere, as I told you, more or less 10 to the 20 particles of a square cubic centimeter. So I thought before I said maybe square centimeter, but I'm wrong, cubic centimeter. Okay. And the interstellar medium, we have so for us on the Earth, it's like a good vacuum that you can reach in the laboratory. And so also, if we speak about, so we need some chemistry, we need particles hit together in order to create something better. And so you can see the collision time scale here in the liquid, in the atmosphere, nanoseconds. Also, you have the possibility that 3 bodies collide at the same time because you have many particles. But here in the stellar medium, so need hours or years for waiting for a collision. So atoms travel a lot, maybe they never meet, they wait years. So the 3-body collision is completely neglected. So the probability to have the 3-body collision is almost equal to 0. Also, this what is liked by chemists. So usually chemistry represent the energy of the molecules. You put the number of molecules here, you put the energy. Usually for the Boltzmann curve, you have like this. Increase the temperature, the distribution is like this. And so some particles have high energy. Most of the particles have average energy. So particle having the low energy is like this. So for the Boltzmann curve, it means that even, for example, you have a chemical reaction, you need that one molecule is 100 degrees Kelvin, okay? So you imagine that in order to make a reaction from A to B, you need to go a step. This step is more or less the energy of the 100 degrees. Maybe you are not at 100 degrees, but some molecules have, maybe you are at 50 degrees, but some molecules have the energy, so the reaction occurs. But here in the interstellar medium, you have different kinetic. So you have not this distribution. And so you haven't the local thermodynamic equilibrium. So you have a different chemistry here.
Sorry, Professor.
Yeah, sure.
It's not clear to me what 3-body collision is.
Where is that? Sorry, there is the 3-body. You're asking about the 3-body?
Yes.
Oh, the 3-body collision is the collision of 3 atoms or molecules at the same time.
Okay, so literally what it's, okay.
Yes, it's
and
a rare,
what does it,
rare
why is it
event.
important for chemistry?
Sorry?
Is there a specific importance in chemistry if they three collide at once?
Somehow.
Okay,
so
thanks.
It's quite rare, but somehow you have. And okay. Okay, let's see here the composition. So we can see the transition between these clouds by seeing the atomic species present. And as you can see, if you have just hydrogen, you can have also carbon ions, so not so useful. Luckily, you have carbon here in this region. You see the name of the Interstellar Medium. But maybe we have to move toward the dense molecular clouds in order to have some interesting chemistry, because at least we have found some molecule that we have on the Earth, even if it's so toxic for us, but at least you have some compound that is more complex than the hydrogen by itself. Even though in these diffuse interstellar and dense interstellar clouds, still you can have the formation of some maybe more complex compound. So the energy is given by cosmic rays at the end. The chemistry is completely different than what you can see here on the Earth. So nobody is able here to work with this maybe nitrogen plus or CH plus. Or maybe chemists have some of these compounds, like compounds forming and immediately breaking up. But you see some interesting molecule, even it has a positive ion. So you see somehow, even though you are able to produce some molecules, even if you're in that condition. So very low energy, so difficult. But in any case, these are observed. So carbon monoxide, water, ammonia, they are formed in this condition. Maybe you spend a lot of years for the forming of this, but still you can have some reactions. So if you go in dense interstellar clouds, it's even better. So you can have also other compounds. Okay, most of these compounds will kill us. So it's so interesting that compounds that maybe give rise to life, they will destroy life now. So today, if you break carbon monoxide, will die. Even the same if you break hydrogen cyanide, but it's so diffuse into the universe. But okay, let's go on. Okay, we see other neutral compound that we can find also on the Earth. See also some complex, also the ethanol, some ether, methanol, and methane, methylamine, acetonitrile, and so on and so on. So you can find something. So you have some clues, some starting point, some starting ingredients for the life. Okay, here we have some differences in these molecular clouds, but okay, here we are just so just to remind what is, I don't want to spend too much time on this slide, but just to tell you that the source of ionization is due to the cosmic rays. As you can see, these dense molecular clouds, it's like black. You cannot see anything. So if you are in the visible, you cannot see anything because you have inside the carbon. And so you have molecules that completely absorb light. So you have to measure this by using radio waves, so microwave radio waves, maybe some IR. And so these are methods to understand. If not, you can see only a black part. And okay, even so, we are speaking about low temperature chemistry. But still you have, I told you, the temperature is very low, so the thermal reaction cannot occur. So usually here we drive all the chemical reaction. If the reaction does not work, okay, hit a little bit. So always work after hitting a little bit. But here you cannot hit anything. So 10 Kelvin is so few, 100 Kelvin, so cold. So the energy of the particles is very low. But you have energy given by cosmic rays, for example, or maybe some UV rays coming from stars and so on. And so you're still able to produce a compound, so another method to see. And so the key of this reaction are some compounds that some chemist is here with me. So seeing by this, it's like, oh, what is this H3 plus? Maybe you're wrong. So if I write maybe in a chemistry exam, I wrote CH5 plus, so my professor will kick me outside the exam. But here we are speaking about some strange chemistry. So these ions can survive because they don't meet, so they meet very rarely. Here on the Earth, if you prepare this, they will immediately hit another compound, will destroy because they will decompose. Okay, in any case, still you can have some, even if you cannot have this, that is so important for the chemistry, still you can form some compounds that maybe have the prebiotic interest. So, what we know up to now. So after many years, you can make a sum up of all the molecules that you found. So molecules means at least 2 atoms, but you can see also 2, 3, 4, 5, 6, 7, 8, 9, 10 or more atoms, also deuterated molecules. This is the presence of hydrogen isotopes. Sorry, I drink some little bit of water. Okay, so as you can see, we almost found, by seeing with the radio telescope, we found almost 200 possible molecules in the interstellar medium. So interesting, even in this harsh condition, so this strange condition, we can have some molecules. And, okay, yeah, I have a list more or less complete of the molecules. I highlighted some of them because they are useful. And then we will meet when we will speak about the prebiotic reaction, because we already spoke about the Miller's experiment. So I think maybe the beginning of the prebiotic chemistry, because nowadays maybe it's different. But what they've done, so they start with some compounds that they are known that it's possible to have in the universe, and they mix together, hope the something will happen. So since carbon dioxide maybe is end point, not a starting point, but still water will be like this. Hydrogen sulfide also is important. Hydrogen cyanide, very important. Even other cyanide, carbon sulfide, important. Formaldehyde, we will speak about this. We'll speak about cyanic acid, ammonia, methane for the Miller experiment, methylenimine, cyanamide, acetonitrile, methanol, formamide, methylamine, glycolonitrile, glycoldehyde. Also, this one is interesting. We'll see why. The urea, acetamide, acetone. Okay, some compound, but oops, what I clicked on, maybe some link that I left. You see also some compound, very strange. So the biggest compound we found, this 6, 7, so these are fullerenes. Still you have fullerenes into the interstellar medium. Then we'll see how they are produced. And also you can have benzene. So I never highlighted this. I have benzene here, benzonitrile. And so you have also strange compound. You have some compounds make like this. So alternance of single and triple bond. These are big molecules you can find here. They can end with the nitrile or not. So these are among the biggest, so the most complex molecules that you can find. So in any case, even if you are low temperature with the low energy, you have all these kind of possibilities. Even maybe you have more, but it's difficult to understand because as I told you, you are just measuring a radio signal. Then in the laboratory, you must understand. So you see, imagine you see one singular signal like this one. So if you enlarge it, you will see a lot of lines. Then how you understand which is the molecule? So you have to repeat the experiment in the laboratory, trying to find the same condition, trying to match all the lines. So it's not easy task, but in any case, it's possible to do. Okay, but we need something more. So we need heavier elements, but we need some solid body for sure. So we need something that is useful to keep some compounds, not let them to float. So maybe concentrate these compounds. If they are solid or possible liquid, they can drive some chemical reaction. So what we know from this, we know that we can have some interstellar grains. So before the solar system formed, you have a lot of interstellar grains. You see, this is this one is like a particle of dust, make probably, I don't know this, but usually in silicon oxide covered by other compounds. And also you have comets. Comets, some of them are very famous, and a lot of space missions send probes to measure what the comets have inside. So we know that they are more or less this like dirty snowballs. So they are composed by snow, so it means ice and other compounds. When they pass close to the sun, so the solar wind make them to evaporate some compounds that will produce the effect of the comet. And so let's focus on this dust grain. So let's concentrate on this grain, because a comet is like a lot of dust grains attached together. So if you understand the chemistry, the physics of the dust grain, maybe we understand the basic physics and chemistry of the comets. So let's start from somewhere. We'll start with the silicate. So silicon is among the compounds that are produced during the blast of supernovas. And so you can have silicates because oxygen is the element is produced in abundance. So all the silicates are more or less solid. So even in the space, if you're at 10 degrees Kelvin, for sure they are solid. So you start from a silicate. It's like the dust that more or less we can have outside. We start from a silicate grain. Then this grain is maybe heated by photons. High energy photons even is heated by hydrogen radicals. So, but what can happen with the hydrogen radical? So usually, so the hydrogen radical meet another hydrogen radical, create hydrogen. But this is it's not so probable, because the pressure is so low. But what happened when one H ion hits this solid silicon dioxide, more or less, it sticks on the surface. So another hydrogen come here, so it sticks on the surface. So they move, they meet, they create some other compounds. It always is happening the same with the carbon ions. So one carbon ion is like rain. So hit the silicon dioxide, sticks on the surface. It means that these surfaces are able to concentrate the compound. So in the gas phase, you have molecules like this. On this grain, you have concentration, because when there is high energy molecules hit, they stick on the surface. And so you have a concentration, you have some chemical reaction occurring in the surface, at the surface of the gas. So the dust grain is acting like a catalyst. So it can increase the speed of the production of compounds. So it's so useful for this point of view. And so at the beginning, you have just simple molecule like carbon dioxide, water, methane, ammonia, and they are solid, because I remember you that the temperature is so low. So they are solid, they stay on the surface. But while it's growing, the next ions will hit not the silicate, they will hit this molecule. And so they will increase the amount of carbon. And so they produce other compounds, they producing carbon dioxide. So at the end, you are concentrating carbon on the surface. And then carbon can undergo other reaction. So because always you have to remind that these grains are heated sometimes by very high energy photons. Could be gamma rays, X-ray photons, UV photon, light photon. So some photons, some nature, they will give some energy. And it's well known, because we can produce this in the laboratory. And it's known that if you start from acetylene in this condition, you will be able to produce some benzene ring, and then the benzene ring will produce other benzene ring, and so on. So you are producing the polycyclic aromatic hydrocarbon, another compound that can be present on these dust grains. I don't know why another compound that is carcinogenic for human beings, so for the animals. So I don't know why all the compounds that are useful for the life, they will kill the life. But in any case, so here we wish to avoid the hydrocarbons, the polycyclic aromatic hydrocarbon. They are U4. Okay, in any case, you have some way to this. And also you can measure the composition of different comets. So some of the comets, famous comets, you measure more or less. So, okay, obviously they are made mainly in water. But you can have some carbon monoxide, some methanol, carbon dioxide. So it changes a little bit from one comet to other one, not too much. So they are more or less matching the composition of interstellar ice, more or less. Okay, not so far from that. So molecules abundant in the interstellar, maybe they are abundant in the comets, more or less, with some differences. Okay, this is a measurement what the scientists see. So they measure this, then they said, oh, like this silicates carbon dioxide, water, methanol, methyl. But I told you, so complex, it takes years to convert this spectrum to something useful. And so, but it's not only the way that we have to measure this. I told you we cannot bring the comet as it's not possible. Maybe one part of a comet, yes. So we have 3 missions. So in the last 10 years, maybe we had these 3 missions. This last gave some sample of, so these 3 gave some sample of some comets and meteorites that are in the solar system. So the first from NASA, the second and third from the Japan Aerospace. And so they collect samples, they brought this to the Earth. So we are able to detect, so that the picture that I showed to you from the Interstellar Medium was collected by these missions, these space missions. As you can see, they are very expensive. They are so difficult to create. Also, you know how it's difficult to reach another planet. Now you're running to take some small object because maybe it's meteorite is like 1 kilometer of diameter. So small, so fast. So you have to reach there with a probe, take a sample, go home. So it's so impressive this that we can do in the last years, but it's possible. So at least we have 3 sample information. And so the important thing is they detected a lot of compounds. For the Stardust mission, that it takes a sample of one comet, they found some glycine, but they are not sure because they are natural amino acids, they are present, so maybe they are source of contamination. They detected a different ratio of isotopes, but there are some doubt that you got the glycine there. But somebody think that you find the glycine on this, so maybe some amino acids for, or at least you can wait. So if you wait, you have some free gifts from the universe. So 10 times a meteorite hit your head, or maybe not your head if not you're lucky. Even we have piece of Mars here. So because on Mars you have volcans and possible they ejected a lot of material, or you have a hit with the impact, and so we have piece of Mars that rained on the Earth. And so from these meteorites, the most important are the carbonaceous chondrites that they are made mainly in carbon. They are rich, very rich in organic compounds, and many of them similar of what we need as the main ingredients for the life. Okay. So let's go on. So this interstellar ice is okay. Maybe we cannot collect many of these interstellar ice, but here in the Earth we can make some simulation. So we can cool down the material in the vacuum, and we can irradiate with UV, and then you can measure. We can measure with the spectrometer in the lab. So easy. We expect to create a space mission. Maybe not so easy to create a setup, experimental setup like this, but still possible. So we can mimic the conditions. For example, we told you the compounds that we saw into the interstellar medium. So water, methanol, carbon monoxide, ammonia, simple molecule. Also, you respect more or less the ratio that you have in the interstellar cloud. So you submit to UV radiation, and you are able to find to detect a lot of useful compounds, cyanides, formaldehyde. This is a hexamethylene tetramine, and also maybe some more or less monomers or polymers, oligomers of this compound. And so here I show you one part is kept from the experiment. You see the original mixture. Here they try several mixtures, and you can find that they are able to detect many other species found. So with respect to the starting composition that is written here, they found a new compounds. And in this experiment, they never heat up the sample. They keep this as very low temperature. But if you heat up a little bit, you're able to find even more complex molecules. So the hexamethylene tetramine, if you heat up the sample even for a few minutes at more or less ambient temperature, you see the spectrum change is big, it's dramatic, because you are producing more compounds. So the starting compound that you form, they react together, creating bigger and bigger compounds, so more complex, so you increase the complexity. So starting from this, we made some experiments many years ago. So we started with the simple things. So acetone water we submitted to, okay, this is the same, but we started from several mixtures, acetone and ammonia and other things. And so after the radiation, with the UV radiation, we are able to find the hexamethylene tetramine. So we made this experiment not at low temperature, but ambient temperature. And so the hexamethylene tetramine, why all people are involved in this hexamethylene tetramine? Because it could be a source of amino acids and other compounds like formaldehyde. So it's like a reservoir or formaldehyde. Formaldehyde is so difficult because it's so reactive. This HMT can release the formaldehyde in the acidic condition. It was used in the past to treat some infection in the urinary tract, because if you ingest this, it will release formaldehyde, will kill microbes. Okay, we know nowadays it will kill also humans because it's so carcinogenic, but okay, leave it. And okay, here we have a comparison in between the thermal and photochemical reaction. As you can see in the photochemical reaction, we obtain, so I don't want to go into detail, we'll leave you this if you want to go further, but we observe different compounds. So the photochemical reaction, as expected, will give you different results. So the photochemical equilibrium is different from the thermal equilibrium. Okay. And then, so what about if you increase the energy of the photon? So if you submit not UV, but gamma radiation, what you will get? Also, again, I see here, if you give even more energy, okay, you produce our friend HMT, so the hexamethylene tetramide. You produce a lot of compounds here. As you can see, thermal reaction, radiation induced reaction, so different, so many possible compounds, because you are with the radiation induced, you have an equilibrium, you can break bonds. So the UV light maybe can break only the bonds that can absorb UV light, but the radiation induced is like breaking all the possible bonds that you can find. So it's like working at high energy. So you break it, but the interesting thing is that you are creating something. So you are creating something that is more complex with respect to the starting materials. You can see here some of the molecules that we detected are of possible interest also. Sorry. Okay, then what we done, we irradiated the hexamethylene tetramide, and we observed what we found. So this is maybe the most interesting thing here. And so we are able to create something that is similar to some nucleobases. So we add some nitrogen and carbon to the hexamethylate. So maybe this clue that the hexamethylate tetramine could be useful also to create the guanine. So I told you amino acids, formaldehyde, I will see later, formaldehyde can give us two sugars. And maybe the guanine, who knows, it's just a clue.